Bismillahirrahmanirrahim. Welcome back to my channel. This video is actually going to be a video on GnuRadio, GnuRadio tutorial series. I think the last video that I made on GnuRadio, which was actually taking how to actually build a transmitter, AM transmitter using those amplitude modulated equations that we normally find in our textbooks. This video is going to be a little bit different. This video is going to be about demodulation of AM signals. So if you were to look at this flow graph, now what is going on in this flow graph is this: that I got this file from internet. Someone has captured a signal using USRP at 710 kilohertz, and this signal was saved in a form of a .data file. Alright, so we're going to learn how to demodulate this data file. So normally when you're making an AM transmitter, and when you're transmitting signal and when you're receiving signal, you can save that signal. Actually, you can listen to that signal live using audio sync, or you can save that in a form of a .dat file, just like this extension, and then you can later on post process your information which is there. So what someone has done, so I got this file which is in a form of a USRP. It was used, USRP was used to capture this file. So this is that file. Now in order for me to demodulate this data file, if you were to look at my flow graph, the next flow graph is actually a rational resampler. Alright, so what does this rational resampler do? Okay, one more critical thing that you need to remember, that if you were to look at the sample rate is at about 256 kilohertz. Alright, why? Because the actual file was captured using that sample rate, so that's why we're keeping it 256 kilohertz, 256 kilo samples per second. Once you know this, all of this, now if you were to look at the second block, which is this is actually a rational resampler block. Now what a rational resampler is sort of like bringing down your samples. It can either lower your samples down, or it can jack up your interpolate your samples. So in this case, I'm using a rational resampler that has a value. So I have used a variable called resamp_factor, so I can just have a value of 4. So I'm calling this value at decimation factor. Now what decimation does is it actually decimate your signal. What does it mean by decimate? It means it's gonna bring your samples down. So if you were to look at this, if we started off with 256 kilo samples, by decimating it, the output of this signal now will have 256 divided by 4, will have 64 kilo samples per second. Alright, once those 64 kilo samples are going in, they are going into a low pass filter. Alright, so we're passing all of this information into a low pass filter. Now low pass filter is not doing anything. It's just taking your samples which are coming in, and the two parameters, I think I have made a video on filters where you can two parameters are important, which is your cutoff frequency. What is the minimum frequency? Anything less than cutoff frequency will be there. I mean, that's the signal that we are interested in. And transition bandwidth is actually the design of your filter. Alright, the wider your filter is, the sharper your filter is. These are the two parameters. So the cutoff frequency is about 5 kilohertz, and transition width is about 500. 500 is just the number 500. Alright, the next block is this. So everything, the file was captured using complex signal. So I need to complex will have I and Q samples, both of them. So but I want to actually see the demodulate. I want to see it. I want to hear that, because we are trying to demodulate this signal, and I want to hear it using my audio sync. So for me to convert from complex to a real form, I'm using a complex to magnitude block. Now all it's doing is actually converting this complex signal into a magnitude, only the real part of your signal. Now the next thing is, the next thing you want to do, if you were to look at this, the next block that you see, which is right here, after complex to magnitude, the next block is going into a DC blocker. DC blocker is just a fancy way of blocking your DC components. That's all it does. If you even put it there, that's fine. If you don't even put it there, that's perfectly fine. Alright, so once you have low pass your filter, now you have your actual signal, the actual signal that you are interested in. You pass it through a complex to magnitude block. Next is DC blocker, just to block any DC component. And I'm using a multiply constant. If it's not there, that's perfectly fine. If it's there, that's perfectly fine. I'm using this multiply constant just to control the volume of my recepted signal. Whatever the demodulated signal is, I'm using a multiply constant block to actually just to vary my noise. I think I forgot to call this, so let me just call this volume. All right, now I'll be able to change this using this QT range block, which I just called. Now the next block is this. We want to interpolate at the same time we want to decimate. So I'm using another what do you call, a rational resampler. Why am I using this rational resampler? Is this that what we're gonna do? We're gonna interpolate our signal. We're gonna multiply our signal by 3, my sample rates, and then I'm gonna decimate by 4. Alright, this is what we're gonna do. We're gonna interpolate our signal and then we're gonna decimate it by 4. Alright, so far so good. So why decimation? Because the next block that it will encounter, the next block that my flow graph will encounter is going to be your audio sync. There are 2 blocks, audio sync, and the sample rate for my audio sync is actually 48 kilohertz. So once I interpolate 3 times, then I decimate by 4. That's mean so I can get a ratio, so I can get my sample rate of 48 kilohertz. Alright, so these are just default sample rate, and I want this sample rate to be 48 kilohertz. This is how things are being sampled. And the next block that I have is actually my time sync, if you can see this. So the next block at the end is 48 kilohertz. Let me just walk you through what's going on one more time. So I have a source, and now the sample rate is being interpolated by 1 and decimated by 4. So now, right now, the actual sample rate was 256 kilohertz. So when it went inside of your low pass filter, it went down by 4. So the samples which are coming out from here is actually 64 kilosamples per second. Alright, because you had 256 which were coming in. It went down 4 times. So the sample rate which is coming out of this block is 264 kilosamples per second. Now after passing through this rational resampler, this 64 is being multiplied by 3. So if you multiply 64 by 3, you get 192 samples. And once you decimate this by 4, you get a sample rate of 48 kilohertz. So this is what your sample rate is for your audio syncs. Now once I demodulate this signal, this is the data that you will get. So let's hear it. So let's see.
Historian from any country as dominant as self has been so far. Well, of course, Mark 6 is winning, won 7 gold medals in 1972, and said, well, historian from any country as dominant as self has been so far. Well, of course, Mark 6 is winning, won 7 gold medals.
Okay, so this is how the demodulated signals sound. Alright, this was an actual data file which was captured at 710 kilohertz, and we have just demodulated this. The thing is repeating itself. Why? Because the repeat block is here at repeat block it says yes, so that's why it just keep repeating itself. So I hope you like this small tutorial on demodulation of AM signal. If you have any questions, leave it in the comment section, and don't forget to like and subscribe to my channel.